Okay, today we are going to talk about trapezoids and kites. Okay, not kits, kites. Apparently I have a typo there. Okay, section 6.5, and what you need to know is we want you to learn to use the properties of trapezoids and kites, and that'll help us find measures of different parts of trapezoids, measures of different parts of kites, and we have a couple theorems that are associated with the regular properties of trapezoids and kites. Okay, so on your foldable, you're going to put half of this on trapezoids and half of this on kites, so that you have some way to organize all your thoughts about all these theorems and everything like this. So this is what we're concentrating on today. We are concentrating on trapezoids, both the regular trapezoid and the more restrictive version of a trapezoid that has one pair of congruent sides, which is the isosceles trapezoid. We will also be concentrating on the kite. Now the kite has no parallel sides, but it's got one pair of congruent sides and angles. Okay, so these two sides are congruent to each other, these two sides are congruent to each other, and then opposite angles may sometimes be congruent to each other. Okay, let's first talk about trapezoids. If you have one set of parallel sides called bases, then you have a trapezoid. Okay, notice these other two sets are not parallel. These non-parallel sides are called legs. So this is a leg, this is a leg. We have a base here and a base here. Okay. Now the two sides that share a base are called base angles. Now these may or may not be congruent. When the legs are congruent though, our base angles will be congruent, and that will be called an isosceles trapezoid. Okay? So the base angles of an isosceles trapezoid are congruent. That is theorem 6-15. Okay, and so with an isosceles trapezoid, when we have two congruent legs, we also have congruent base angles. Okay, now we also have another set of base angles here. Okay, and those will also be congruent. Now, another thing to notice, theorem 6-16, the diagonals of an isosceles trapezoid are also congruent. So this is congruent to this. Okay? Now they do not bisect each other, but the full length of the diagonal of each diagonal is congruent to the other full length. Okay? Does that make sense? Hopefully so. And that is theorem 6-16. Okay, so here we have an example here. We're given polygon ABCD with the current markings. We're given that the measure of angle A equals 55 degrees. Segment BD has length 2x minus 4, and segment AC has length 4x minus 12. Okay? So this is an isosceles trapezoid because side BC and side AD are parallel, and sides AB and side CD are congruent, okay? Which means that our base angles are going to be congruent. So if measure of angle A is 55 degrees, then measure of angle D will be the same thing. So measure of angle D is equal to 55 degrees. Now we also need to know measure of angle B and C, right? Now, we know that they're going to be congruent to each other because base angles of an isosceles trapezoid are congruent, but we don't know what that is. Well, if we know that BC and AD are parallel, then AB is a transversal. And measure of angle A and measure of angle B, because they're on the same side of that transversal, will be supplementary. So 180 minus 55 will be 25 degrees. Okay? Sorry, 125 degrees. What was I thinking? 125 degrees. Something wasn't computing in my brain, and I'm like, wait, that's got to be an obtuse angle. Anyways, so 125 degrees will be the measure of angles B and C. Now, we also need to know the side lengths of BD and AC. Because it's an isosceles trapezoid, we know these two side lengths are congruent. So we know that 2x minus 4 is equal to 4x minus 12. Subtracting 2x from each side and adding 12 to each side to move everything around, we end up with 2x is equal to 8. Dividing by 2, we get x is equal to 4. Plugging back in, we get segment BD. I wanted the eraser, not. We'll go with it. Segment BD is equal to 2 times 4 minus 4, which is equal to 8 minus 4, which is equal to 4. Now AC should come out the same length. AC is 4x minus 12, which is 4 times 4 minus 12, which is 16 minus 12, which is 4 units, whatever those units happen to be. We haven't attached units to this, but 4 units of whatever we're measuring in, okay, will be the length of both BD and AC. So hopefully that helps you work through some isosceles trapezoid problems. That will be basically the gist of most of the problems dealing with theorem 615. So using those base angles of isosceles trapezoids being congruent, and then theorem 616, which uses the fact that diagonals of an isosceles trapezoid are congruent. Okay, so that will be what most of our problems are like. Let's move on to kites. Well, kites have no parallel sides, but our adjacent sides are going to be congruent. So if we're drawing a kite, I think I meant to put a figure of a kite in here and I got distracted and never came back to it. We know that adjacent sides are going to be congruent, like this, and then opposite angles will be congruent. And by opposite angles, we mean the angles right here and right here. Okay? Now, we may or may not have these two angles congruent. If we do, then it becomes a rhombus, and hence a parallelogram. But we have one set of opposite angles that are congruent. Okay? Now, another thing that we know is that our diagonals are perpendicular, and this is in conjunction with theorem 6-17. So if I draw in these diagonals, not congruent, they'll be perpendicular. Okay? They don't bisect each other, they don't do anything special like that. Their special relationship is the diagonals are perpendicular, which is great because it then divides this kite up into 4 right triangles, which means we can use our right triangle postulates to help determine lengths and angle measurements of triangles formed within the kites by the diagonals. Okay? So, we know that the top two of our triangles are going to be congruent, and the other 2 of our triangles will also be congruent. They may not be congruent to each other, top and bottom, like these 2 sets may not be congruent to each other, but we'll have 2 sets of triangles that are side by side that are congruent to each other. If all 4 are congruent to each other, we have a rhombus. But if they're not all 4 congruent to each other, we just have a regular kite. So that can help us with all these properties, can help us solve problems regarding kites. So here we are given kite ABCD, and we're given that BC has length 3x plus 6, and CD has length 7x minus 2, and we want you to find x. Well, since it's a kite, we know that adjacent sides are congruent. We also know that the diagonals are perpendicular. So we know that BC is going to, length side BC is going to be congruent to side CD. Does that make sense? Which means 3x plus 6 will equal 7x minus 2. Subtracting 3x from both sides and adding 2 to both sides, we get that 4x is equal to 8, so x is equal to 2. So x is equal to 2, that's what we need to find, and we want to check that by making sure that x equals 2 really results in BC and CD being congruent. So 3 times 2 plus 6 should equal 7 times 2 minus 2. So 6 plus 6 should equal 14 minus 2, and 12 does equal 12, so x equals 2. Now what this does is this creates two congruent triangles, and I'm just extending this example here because we have the reflexive property here. And so by the hypotenuse leg theorem, triangle CEB is now congruent to triangle CED, okay? So I hope that makes sense to you in proving like that inner triangles of kites are congruent, okay? So we've learned trapezoids and isosceles trapezoids have similar properties, but isosceles trapezoids have special properties that make them easier to work with, okay? Also, kites have properties that allow triangle congruency postulates to be used to find missing sides, angles, and diagonals. We did not do that as part of a example problem, but it could be done, okay? And we did show you how to use the hypotenuse leg theorem with that. So that's it for now for kites and trapezoids, and examples are also in the book if you care to look at those as well. And have a great day.